Hello, so in this video I want to talk about a special type of non-linear first order differential equation. Okay, so normally we're used to seeing a first order differential equation looking like this. So in other words, we have the first derivative plus some coefficient which can vary times by our function, and that's normally equal to something which is involving t on the right hand side, or at the very least it will be 0 on the right hand side. And this is what's known as a linear first order differential equation. It's first order because the highest derivative is 1, or the first order, and it's linear because we've got the first derivative and the function, and anything involving t kind of written separately. So we're not, you're not, for example, multiplying the y by the first derivative, for example, or we're not raising y to some power, so not raising y to, say, the power 2 or something. This is what makes it linear. Okay, so this is a linear case, and normally we just deal with linear cases, okay, where we kind of steer clear of the non-linear cases because they can be a little bit awkward and a little bit tricky to deal with. We usually tend to solve them. We usually resort to solving them by techniques such as numerical methods. So, in other words, using a computer to kind of guess. It's essentially just glorified trial and error, right? But there is a special type of non-linear first order differential equation, and it's a type called Bernoulli's equation. And there are these kind of special equations in differential equations that kind of would otherwise be would be quite difficult to solve, but basically because they've been looked into, we can basically just employ some technique or some special trick which makes it easier to work with. Okay, so here is how Bernoulli's equation works. So we've got the first derivative, well, that's still looking like our first order linear differential equation, okay, plus some coefficient times our function. Now, up to now, that is still looking like our first order linear differential equation, the thing which we're used to looking at, linear case. Okay, and that's equal to q of t. Again, this is exactly the same as we would have as a linear case, but we have one small little addition. Well, I say one small little addition, actually it makes a pretty big difference. And it's this y, we multiply by y, and we raise it to the power of n. So this term on the end, immediately makes it non-linear. Okay. Now, ordinarily, if you just kind of get presented with that, you think, well, it's non-linear, it's going to be quite awkward to deal with. Okay, and if you kind of try and employ the traditional techniques that you're used to, then yeah, absolutely, I would totally agree with you, right? But actually, what we can do is we can employ a little trick to make this slightly easier to deal with. But first of all, let's look at the case when n equals 0. Well, when n equals 0, what do we end up with? We end up with first derivative plus this thing times y equals q of t times y to the power of 0. So that's just going to be 1. So that then, when n is 0, it's just linear. Okay? And likewise, when n is 1, we just end up with y to the power of 1. So it's going to be y, okay? And this is still linear because look, if I take this over to the other side, what do I end up with? I end up with this, okay? And then if I just factor out a y out of this thing, okay, that now, if I just write this whole these two coefficients being subtracted from each other, if I just write them as one coefficient, so I kind of combine them into one coefficient, let's call it a of t, then that becomes a first order differential equation, and it's actually a homogeneous case. So the case when n equals 0 and the case when n equals 1 basically reduces the Bernoulli equation, this thing, down into a linear first order differential equation. Okay, so in other words, what we want to do is we want to consider the case, but for all other values of n. So when n is not equal to 0 or 1, then therefore what do we get? Well, we get a non-linear first order differential equation. Okay, so in other words, we kind of consider that. Right, but what we can do is we can employ a special trick. Okay, we can introduce a special trick, and the special trick is by basically making a substitution. Normally these kind of things, the special tricks are usually, especially in differential equations, are normally based around making a substitution. I mean, we're going to come on to talking about reduction of order in a few videos' time, and that is literally by making a substitution to make, it's a second order, to basically convert a second order differential equation to a first order differential equation. But there we are. So basically the idea is that we introduce a new substitution, and we're going to call that new variable, effectively, that we're going to introduce. It's actually going to be a new function. We're going to basically replace we're going to call v, and we're going to call it y is 1 raised to the power of 1 minus n. So in other words, we look at this, the thing which makes it non-linear, okay, and we basically make a substitution. So from this thing that makes it unlinear, we find n, okay, and then we make a substitution, and this is the substitution that we make. We say that v is just going to be y to the power of 1 minus whatever that power is up there. Okay, so the best way of kind of seeing this is via an example. So let's pull up the example. So here's our example. Here is our example. Okay, now as you can see, this is non-linear because of this term here. This term here makes it non-linear because it's y cubed. Okay, it's not just a single y. You know, y is now being raised to some power. So the general form for a Bernoulli equation is like this. It's like this. So we got this thing going on. Okay, and the substitution that we want to make is v equals y to the power of 1 minus n. So in other words, we need to know what n is. Well, n is given by the thing which y is raised to. So in this case, y is raised to that. I mean, I can make this thing look a little bit more like that just by taking this minus y cubed over to the other side. Okay, so otherwise I can make this equal to y cubed. Yeah, I've just taken it over to the other side. Okay, so now hopefully you can see that, you know, my coefficient, my q of t, if you like, is at the moment is just 1. Okay, I haven't strictly got it looking like this because I haven't got anything in front of in front of this thing here. So the next logical step to do is to basically get rid of this coefficient in front of the y to the power. The first derivative of y. It's not the power of 1. It's y prime. Okay, first derivative of y. So basically, what I'm going to do is I'm going to divide. I'm going to look at this thing. This is at the moment, you know, this has got a coefficient of t squared. I don't want any coefficient there. So in other words, what I'm going to do is I'm going to divide everything in this equation. I'm going to divide everything in this equation through by t squared. So in other words, if I divide everything through by t squared, this is over t squared, and this is over t squared as well. Okay, so now I've got just a single, you know, I haven't got any, it's a monic equation. Okay, I haven't got anything, or I've just got a 1 in front as the coefficient in front of that y dash, which is good because it's looking a little bit more like that. Okay, I can do a little bit of simplification here. Okay, I can look at this term here, and I can just say, well, that t will cancel off with that one of those t's in there, so it'll just be left with 2 over t. Just be left with 2 over t. Okay, so this is now looking a little bit more like it. Okay, because now my p of t is 2 over t. Okay, and my q of t is 1 over t squared, and my n is going to be 3 because I'm looking at that power there. Okay, so therefore I know that the substitution I'm going to make is v equals y to the power of 1 minus n, where n is 3. Okay, so therefore this is going to become 1 minus 3, which is of course going to become minus 2, or I can write that as 1 over y squared. It's whatever kind of, it's whatever form you prefer. Okay, either one is absolutely fine. Right, okay, so I'm going to make this substitution. So v equals 1 over y squared is the one which I'm going to deal with. And so basically now what I'm going to do is I'm going to make my substitution. So I'm going to make my substitution with the sole aim of trying to get rid of my y. So I'm going to make a substitution for y. So in other words, what I'm going to do is I'm going to rearrange this to get y equals something in terms of v. So then I can just replace y in there and the y in there. Okay, so let's have a look. See what I can do. So let's have a look. Let's see if I can rearrange this. So I'm going to end up with y squared equals 1 over v. Okay. Okay, and then I'm just going to find it in terms of y. So y is equal to it's going to be square root, and I can have the plus or minus square root, remember, of 1 over v. Okay, and I'm just going to write this for the moment as it's going to be 1 over v to the power of a half. Okay, and this 1 over v is just going to be written as v to the minus 1. So therefore, this can just be written as v to the power of minus a half. Okay, and there's a reason why I'm writing it like that. Because notice that I want to find, I want to basically try and make a substitution for this highest power. It's the highest derivative, which is 1. So I want to try and make a substitution for the first derivative of y. So the first derivative of y, so y dash, okay, I'm just going to write that as dy by dt. So I want to make a substitution for that. Well, look, I can do that because I've introduced a new variable. Well, I've introduced a new variable to kind of for y. I've introduced a new variable. So kind of whenever I introduce a new variable and I want to find the derivative of something for which I've replaced with a new variable. So, for example, I've used y. Where are we? This thing here. So I've kind of replaced y with a new variable. Yeah, I've replaced y with a new variable, and I want to now find the derivative of y. I want to find the derivative of y. So whenever I introduce a new variable, and then I want to differentiate, with respect to my old variable, but I've introduced a new variable in its place, always think the chain rule. So whenever I make a substitution, chain rule is your friend when you want to find the derivative of something. Okay, and the chain rule basically works. Chain rule is a really nice rule because it basically works by a fraction. Okay, so it allows me, because I've introduced a new variable, it basically allows me to introduce a new term into my derivative. Okay, let me try and show you what I mean. So I want to end up with something that equals dy by dt. I'm just going to treat this as a fraction. Okay, so basically if I want dy here and I want dt here, so I'm going to split it up into two fractions being multiplied together. So this is going to give me my dy by dt. My dy by dt, and whatever goes here and here needs to be the same. Well, I've introduced a new variable, so it makes sense that my new variable will go in here. So my new variable is dv, or my new variable is v, but of course I'm differentiating, so I'm just going to stick a dv in here. I mean, I always, a really good tip is just to treat this as a fraction, differentiation as a fraction, okay, because that will get you out of Lord's place. And this is basically all the chain rule is. This is all the chain rule is, because it causes a cancellation in there. And so what am I left with? Well, I'm just left with dy times dt, yeah, which is fine. But, this kind of introduction of a new variable is exactly what I want to do. Because, look, I know what dy by dv is. I know what dy by dv is. Because, look, I've got y in terms of v. I've got y in terms of v, which means I can differentiate y with respect to v. Because look, if I say, well, what's the derivative then of y with respect to v? It's just going to be the derivative of that. It's going to be minus a half v to the minus 3 over 2. Minus a half v to the minus 3 over 2. So therefore now when I want to try and find the chain rule, okay, what I can do is I can just replace this dy by dv by this thing in here now. By this thing in here. So I will end up with minus a half v to the minus 3 over 2, okay, times by dv by dt. I don't know what that dv by dt is, but if I rewrite dv by dt as just v dash, because that's effectively all it is, then I made, that's absolutely fine, okay. So let's have a look now. So what can I do? So let me just write this thing out again. Okay, so this is everything which you know up to now. Basically, I'm working with this to try and hopefully make an amazing substitution. It just suddenly makes this a whole lot easier to deal with. Okay, well, it's very, very close. The only other thing which I want to do, and it may seem a bit counterintuitive, but I'm going to do it anyway, because it's kind of the easiest way that I can probably show you, is notice here, is I want to work with this bit a little bit more. So I end up with minus a half v to the minus 3 over 2. I'm actually going to say that that's v to the half times 3. So in other words, this is just by power laws, it's just v to the power of minus a half cubed. Okay, so that's all that bit in there is. There, and then of course that's times my first derivative, okay? And the reason why I've done that is because, look, I've said y is equal to v to the minus a half. So in other words, I'm just going to replace that by y. So what do I end up with? I end up with a half y cubed times v dash. Okay, so I'm just going to make that substitution now. So y prime, so I'm going to replace y prime, that thing there, with all of that, okay? So let me just do that then. So I end up with, hold on a minute. So I'll just write it out again, so then you can hopefully refer back to the original one as well. So I'm just going to replace that with all of that. So in other words, minus a half y cubed times v dash. Yep, times v dash. Right, okay. Then what I'm going to do is I'm going to divide everything. By y cubed for the moment. I'll deal with the this thing a little bit later. But I'm just going to divide everything through by y cubed. So in other words, I'm going to divide that by y cubed. I'm going to divide this by y cubed. Oops. Divide this by y cubed. And I'm going to divide this by y cubed. Well, look, this is really, this is, and in truth, this will always work. But basically, by making that substitution, it causes a lot of cancellation. Because look, these two things cancel off. So effectively, I've got rid of, that thing on the right-hand side. And this thing, look what this thing reduces down to. I can cancel one of those off with one of those off. Okay, so this then becomes 1 over y squared. Well, I know what 1 over y squared is. I know that v is equal to 1 over y squared. So in other words, I can just replace that with v. Look what I've ended up with. I've ended up with a first-order differential equation just involving v now, okay? And it's a first-order linear differential equation, which means that I can work with it really, really easily. Okay, the only other thing that I do want to just kind of do just for tidying up's sake is get rid of that. I want to make that, you know, the coefficient in front of the v dash, the first derivative, I just want to make that 1. So in other words, I'm going to multiply through by minus 2. If I multiply through by minus 2, then I'll get rid of that. So if I multiply through by minus 2, because look, if I multiply through by minus 2, that becomes a plus 2 over 2, so that cancels. Okay, this then becomes a minus 2 times 2, which is 4, and then this becomes minus 2 over t squared. Minus 2 over t squared, okay? Okay, so then this is just now my standard first order linear differential equation, okay? So, in other words, it's of the form, if you remember, it's of the form, I've used p's before, but basically, you know, it's of the form y dash, or I'd keep the v. I'll keep it with v. I was going to introduce the general form of, you know, the first order linear differential equation, but I'm just going to try and write it like this. So plus some coefficient times my function, which is now v, okay, is just equal to something on the right-hand side, which I'm going to call b, okay, and therefore this is because it's of this form, because you can clearly see that, you know, my a of t is minus 4 over t and my b of t is minus 2 over t squared, then therefore it allows me to make use of something called the integrating factor. And the integrating factor is just e to the integral of whatever this coefficient in front of my function is. Just, you know, no derivatives or anything, just my function, my plain old function v. Okay, so my a of t, in other words. So my a of t with respect to t. Okay, well, what is my a of t? My a of t is this thing here. It's minus 4 over t, because that's the thing being multiplied by v, or that's the coefficient in front of v. This is e to the integral of minus 4 over t with respect to t. Okay, so can we work this out in your head? Well, have a think about it and see what happens. So just pull this up. It's dead straightforward. It's basically e to the integral of this thing. Well, if I take a minus 4 out the front, that just becomes the integral of 1 over t with respect to t. Well, the integral of 1 over t with respect to t, hopefully you all know, that is just the natural logarithm of t. Okay, 1 over t, it's just the derivative of the function over the function. Okay, and therefore I'm just going to, by power laws, or do I even need power laws? Not necessarily. If I just swap these two things around, okay, I'm trying to show you what this becomes. Hopefully you can already see it, but I'm trying to show you what this becomes. This is minus 4 times the natural logarithm of t. So I'm just going to swap these two things around. In other words, I'm going to write e to the ln t all times by minus 4. Yeah, because that's all times by minus 4, and that's going to be exactly the same as what I had before. So therefore, this is going to become e to the natural logarithm of t is just going to become t. Yeah, I've shown you that a few times before. If you have y equals e to the ln x, okay, e to the ln x, then if I rewrite this thing, so the power is the subject of the formula. So ln x is going to be log to the base e of y. So that's just natural logarithm of y. Okay, therefore you can just see that the two things in the brackets are the same. So therefore x equals y. So therefore if x equals y, then this thing is just equal to x. So in other words, I just look at the thing inside the natural logarithm. Okay, just another proof again, because it's quite a nice simple proof to do. So this just becomes t, okay, raised to the power of minus 4. T raised to the power of minus 4. So that's now my integrating factor, t to the power of minus 4. And I'm actually going to write this as 1 over t to the power of 4. Okay, so this is now my integrating factor. Remember the whole idea behind integrating factor. If I just rewrite this perhaps as dv by dt, then hopefully you can see it. If I want to basically multiply everything through by mu, okay, multiply everything through by mu, so this becomes d dt of mu times v. Okay, these things in the middle effectively cause a cancellation, so we don't have to worry about that. Is equal to mu times, you know, my right hand side. So this is my right hand side here. So mu times minus 2, so I'm going to write it like this, minus 2 over t squared times mu, which is 1 over t to the power of 4. Okay, power laws again, just multiply those two things together. It's going to become t to the power of 6. This is 1 over t to the power of 6. Okay, I therefore just rearrange that. So if the derivative of that is equal to minus t to the power minus 2 over t to the power of 6, then therefore this mu v must equal to the integral of this. Okay, well the integral of this is going to be, well this is technically minus 2t to the minus 6, okay, raise the power by 1, so it goes to t to the minus 5,
okay, and divide by that new power. So divide by minus 5, and I've already got a minus 2 sitting there. The minuses cancel, and I don't forget your constants. So I'm going to say plus C1, because I don't know how many constants we're going to end up with. Okay, so this is what mu v is equal to. Well, what's mu again? Mu is 1 over t to the power 4, so 1 over t to the power 4. So 1 over t to the power 4 times v is equal to that. So therefore v must equal t to the power 4 multiplied by all of this thing. T to the power 4 multiplied by all of this thing. Let's see if I can do a little bit of simplification here. So end up with t to the power 4. I'm going to rewrite this thing in here as 2/5 times 1 over t to the power 5. So let's just condense those two things together. So it's going to be 2 over 5 t to the power 5. Yep, plus some constant. So plus some constant C1, sorry. And I'm just going to multiply through by t to the power 4. So this becomes 2 t to the power 4 plus C1 t to the power 4. Okay, I can do a little bit of cancellation. I can cancel off 4 of those t's and just leave 1 on the bottom. So end up with this thing. Okay, but remember v. So v is equal to that. But remember what v was equal to. Remember what v was equal to. V was equal to 1 over y squared. V was equal to 1 over y. So therefore, and I worked out as well that y was going to be equal to the square root of 1 over v. Yeah, just from rearranging those two things. So therefore, if v was equal to this thing here, then therefore y must be equal to the square root of 1 over all of that thing. 1 over all of that thing. Can I do much with that? Well, yes, I can, but I'm going to leave it like that for the moment. So t over 5 to the power 5t plus c1 t to the power 4. Okay, can I do much with that? Yes, I can. I'm going to actually try and write this as one fraction on the bottom now. I'm going to try and do a little bit tidying up on the bottom just to make this look a little bit tidy. I mean, that is my answer. That is absolutely my answer, but I'm going to try and make it look a little bit tidier. I'm going to make it look a little bit tidier. So I want 5t on the bottom here. So I basically want 5t on the bottom. Well, in order to have 5t on the bottom, I'm going to have to multiply by 5 here. I'm going to have to multiply by 5t here. So this becomes that. Okay, 5t here. So now I can write this over the same thing. So it's 2 plus 5c1 t to the power 5 over 5t. Okay, and it's 1 divided by that. So it's 1 divided by 2 plus 5c1 t to the power 5 over 5t. So therefore it's 1 divided by that. If I just flip it up the other way, then this then becomes a times. This then becomes a times. So therefore, what's inside the brackets here? It just becomes this. So it's 5t over 2 plus 5c1 t to the power 5. 5c1 plus t to the power 5. And actually, I'm going to rewrite this because effectively it's just 5 times some constant. 5 times some constant is still going to be a constant. Okay, it will also automatically be taken care of. So I'm just going to call that c2. Okay, so that's basically what y is equal to. So, I mean, basically the whole idea behind Bernoulli's equation, is effectively this. You make a substitution for that, okay? You then try and get sort of your Bernoulli equation in this form, okay? You make a substitution for that, okay? You then try and work out the first derivative, and then everything else will just kind of follow. Everything else will just kind of fall out from there, okay?